So we are going to start with transformations, and specifically today we're going to start to look at reflections and see what each of these transformations do and learn some basic vocab associated with it. So we have 4 pictures that we're going to take a look at. It says the image of the rabbit face. It's been transformed each time into image B. So we're starting at A, transforms it into B. We're going to match the transformation with its proper name. So for this first one, I can see I'm starting at A and I'm sliding up to B. That slide, that's that translation. So I can say this first one is a translation. The second picture, starting at A, going over this line to B, and I can see it looks upside down, that's going to be a reflection. And I can see maybe a little bit more detail. I can see these lines, if I were to connect them, they're going to be the same distance into the line of reflection as it is out from the line of reflection. If I were to measure the distance, let's say from this side, same distance into the line of reflection as it is the same distance out from the line of reflection. For this next picture, starting at A, I can see this turn kind of happening, some sort of a twist that's going on, so that's going to be our rotation. And I can see that there's a fixed point, it's a center point, that center point's not moving. And our last one, I can see a picture starting at A going to B, it's gotten much bigger. So that is what's called a dilation. Could get bigger, could get smaller, it's changing the size. So we have just identified 3 of these last 4 have been what's called a basic rigid motion. And what that is some sort of a transformation that preserves, and by preserving we mean it doesn't change. So preserves, I'm going to say shape and size, but when I say shape, I think shape, we know what I mean. If it's a triangle, it stays a triangle. If it's a square, it stays a square. When we get into size, now we want to think with size, there's 2 really important things here. The side length doesn't change, and the angle measure. So if I can look at these shapes, and when I'm transforming them, if we're saying preserve size and shape, the size you want to clarify, and you want to make sure you're saying the side length and the angle measure will not change, or they are preserved. So examples that we have here, we have our reflection, we have a rotation, and then we also have our translation. So those 3 are our 3 major examples of basic rigid motions. Doesn't change the size, doesn't change the shape. Now an example that's not a rigid motion would be our dilation. And our reason is because it changes our size. And in particular, it would change, now again, like when we said size, maybe it changes the side length, making it perhaps bigger or smaller. So it changes size, side length in particular that we're looking at. It could get bigger or it could get smaller. So think dilation, when your eyes dilate, they get bigger, they get smaller. Okay. 2 other words that we're going to take a look at on the next page are what's called a pre-image and an image. So from that first example, maybe we'll flip back there. Our first example, all of our A positions of the rabbits, these were our pre-image. And when we get to B, this is what's considered our image. So if we're going to put that into a vocab word, our pre-image, that's our starting figure. Okay. Maybe we want to think of it's what happens, it's before some sort of a transformation. Okay. Our image is going to be the resulting figure. And this is going to happen after the transformation has taken place. So if I want to think about this, maybe simpler forms, our pre-image, that's where we start, and our image is where we stop. So that'll come up a lot in questions, and we have to just be careful with our vocab and just be aware of those words. So we'll try some examples down here. So ABC has been graphed, and we have our vertices labeled, and it says we're going to use the following rules to produce two different triangles, A prime, B prime, C prime, and then A double prime. And we're using the original image each time. So every time we're starting, we're going back to that original image. So if we're looking at this, and we can do this one of two ways. We can either do it graphically or numerically, and I'll try and show you both. For instance, if we were to start at A, so we know A's coordinate is -4, 5. And looking at this, it says I want to take this value, and to -4, I want to add a 2. And to the -5, I want to negate it. Okay, so if we did this transformation, it tells us our final image is going to line up at -2, +5. And this would become A prime. So if we go over -2, up +5, and I put a point, I'm going to see that that is, oops, I have a mistake here. It started off positive, I apologize. And then when we negate that 5, it will end up negative. So if we go over a +2 and we go down 5, this is our A prime. Okay, we'll try B prime. So B starts off at -6, -4. So when we do this transformation, I have a -6, I want to add 2 to that x coordinate. It says take my -4 and negate it. So -6 + 2, that gets me a -4. A -4 turns into a +4, and now here's B prime. So I'm going to go to the left 4, that's -4. I'm going to go up 4, and that's going to get me B prime. Make sure we label. Now we can also kind of do this graphically. If I started C, to C it's saying add 2. So in other words, go to the right 2 units. So that would put us here. And then it says negate the Y. Well, if I'm negating the Y value, that means we'll do the opposite. In other words, we're going to flip over the x-axis. So I would think flip over the x-axis, which would put me here. Notice again, the distance to the x-axis, it's the same each time. This becomes my C prime. And we can do that algebraically as well. Sometimes graphically is easier, sometimes it's not. Just give you options on how to solve. Okay, we're going to take a look at letter B. And with letter B, now we have a different idea of what's going on. So it says I'm going to take my x value and cut it in half. And to my y value, I'm going to add 5. So again, starting back with A. So A is starting at -4, 5. It says what I'm going to do is take -4 and cut it in half. And to the y value, which is 5, I'm going to add 5. So half of -4 gets me a -2. 5 + 5 will give me 10. And there's my A double prime. So if we were to graph that out, I would go to the left 2, and I would go up 10, and here's A double prime. Okay, we're going to try the same with B. So B starts off at -6, -4. I'm going to take -6. It says take half of that. Take my -4 and add on 5. So this would get me -3. And then when I add those two, I'm going to get a +1. Here's my new B double prime location. So I have a -3, I have a +1. Here's B double prime. Notice color at these times can be helpful as well. So we'll start off with C at -4, 4, and again, we're going to do that same transformation. So I have 4 divided by 2. I'm going to take my y value of -4 and add on 5. So when we simplify, we're going to have 2, we're going to have +1, and now that's C double prime. So we're going to go over 2 to the right, up 1, there's C double prime. So here's my new image. So the black triangle was our pre-image. The red triangle and the blue triangle, those are our image. And now for letter C, it says which of these two transformations maintain the shape and size of the original image. Well, if we take a look, the one that looks to be the same size, that's going to be our first transformation. We could say that f function. So the triangle a prime, b prime, c prime was the one that maintained it. And now since it maintained that shape and size, we can say that this is a basic rigid motion. Okay, our next picture. We're going to try another one. So first we want to graph triangle ABC. We want to make sure that we're labeling it. So if I go to the set of axes, we're going to graph this out. A is located at -5, +1, so make sure we label. B is at -1, +1. And C is at -1, +7. And now we're going to connect our lines. So we have our triangle. And that was part A. On part B, it's saying we're going to take this and we're going to reflect this over the x-axis. So if we reflect these over the x-axis, I want it to go on the opposite side. So right now it's above the x-axis. So if I reflect it, it needs to go below. And we had pointed this out in the beginning. What you're going to notice is the distance to the x-axis, which is only 1 unit, is the same amount that you're traveling out. So if I do the same thing at B, I travel 1 into the x unit, I travel 1 out. Now for my C coordinate, I have to travel in 1, 2, 3, 4, 5, 6, 7. Means I have to travel out 1, 2, 3, 4, 5, 6, 7. And here's my C coordinate. Now if we were to take a look at the actual coordinates themselves and see what has changed. So if I look at A prime, I can now see A prime is a -5, -1. And B prime is a -1, -1. And our C prime turns out to be -1, -7. So if we were to compare these with our original values, we can see when we are reflecting over the x-axis, the only thing that's changing is our y values are now negated. So maybe that's a rule that we want to keep in mind. If I reflect over the x, I want to think change the y. Okay, we're going to take a look at letter C, and it says on the same set of axes, we're going to graph A double prime, B double prime, C double prime, the image of ABC reflected over the y-axis. So we're starting back with our original triangle. This time I want to reflect over the y-axis. So same idea, the same number of units in is the same number of units out. So there I can see that's B double prime. Let's take a look at C. I go 1 unit in, I go 1 unit out. For A, I have to count in 1, 2, 3, 4, 5 units, which means I have to count out 1, 2, 3, 4, 5 units. And now I can see that the shape has been reflected over the y-axis. We're getting that mirror image look. And again, if I look at the coordinates, just to kind of see what's going on, I can see A is now at the location 5, 1. Our B value, B double prime, is now at the location 1, 1. And I can see our C double prime is now at the location 1, 7. So again, if I compared these to our original coordinates, I can see that if we are reflecting over the y-axis, it looks like at this time our x values negate. They become opposite. They switch their signs. And the last thing we're going to do is we're going to take a look at perhaps constructions based off of this. So with these constructions, we want to construct a segment that represents the line of reflection for this quadrilateral and its image. So I need to find something that's going to be showing me perhaps the middle. I know it's got to be somewhere in the middle if I were to take that. So what I'm going to do is I'm going to start by saying let's connect C to C prime. And we're going to do that with a nice straight line. So make sure you have a straight edge as you're doing this. Then we need to get our compass. And what we're going to do with our compass is we're going to create a perpendicular bisector. And the way we do that, if we remember, is we want to take our compass, open it up so that it's more than halfway. It can go all the way to the end, kind of like this one does. And we're going to create an arc top and bottom. And I'm going to flip it around. Same thing, bring my compass over to the other point, create that arc top and bottom. And with a nice straight line, what I'm going to be able to do is connect those points of intersection. And by doing that, you have just found your line of reflection. Now we connected C to C prime. You would notice the same thing would happen if I connected any of these. If I connected B to B prime, that same construction would work. So in order to find that line of reflection, you're always doing the perpendicular bisector. So it says what's true about each point. We can say that they have to be equally distant from our line of reflection. If it's on the bisector, it's going to be the same distance from each side. So important facts to keep in mind. The line of reflection is the perpendicular bisector of the segments connecting the pre-image, our starting figure, to our image, our ending figure. Each point and its image point are equidistant from that line. And these last two, our reflection carries segments onto segments of equal length, meaning it preserves size. So we had talked about that when we said preserves the side length measure. That's what this is talking about. And a reflection carries angles onto angles of equal measures. So when we had said it preserves angle measures, that's just a different way to say this, preserves angle measures. So this is our brief intro into transformations and reflections in particular, and we are going to work more with this in class and see some more things that we can do with this as far as constructions and creating new shapes.